In today's video, we're going to walk through a natural language processing project from start to finish by doing sentiment analysis on Amazon reviews. Sentiment analysis is the use of natural language processing to identify the emotions behind text. We're going to walk through a traditional approach to sentiment analysis using Python's Natural Language Toolkit, or NLTK. And then we'll implement a more complex model called RoBERTa that's provided by huggingface. We'll do some analysis of how the different models perform, and we'll even explore using some pre-trained pipelines for making sentiment analysis really quick and easy. Hi, my name is Rob, and I make videos about data science, machine learning, and coding in Python. I'm going to share everything we do today in a Kaggle notebook, so you can find the link in the description, copy that notebook, and explore all the stuff that we do today. If you do enjoy this video, please consider subscribing, liking, and follow me on Twitch where I stream live coding. All right, let's get to the code. Okay, so here we are in a Kaggle notebook. You can see this is the basic outline of what we're going to be talking about today. We're going to be doing some sentiment analysis in Python, and we're going to use two main techniques. The first one is the older kind of way of approaching sentiment analysis with a model called VADER, and this uses a bag of words approach. And then we're going to look at a pre-trained model from Hugging Face that's a RoBERTa type model, and this is a more advanced transformer model that we're going to see how the results compare between those two models. And then we're going to also explore a Hugging Face pipeline. But before we get into that, let's talk about the data and do some basic analysis with the Natural Language Toolkit, which is a great library for Python. I'm going to show you over here to the right side that we are going to use this data set that is a bunch of Amazon fine food reviews. So these are text reviews for food on Amazon, as well as the rating that out of 5 stars that the reviewer gave them. And all of this is in CSV format that we're going to pull in. So before we get too far into it, let's do some of our imports. We are going to, let's give it some space here. We're going to import pandas as PD. We're going to import numpy. For some plotting, we'll import matplotlib. pyplot as plt, and we're going to import seaborn as SNS. Let's set a style sheet that we'll use for our plots. And then we're going to, just to start out here, import NLTK, which is that natural language toolkit we'll be using for the start. Let's go ahead and read in our data. So let's comment here and say read in data. And we're going to read in from the input directory. There is this reviews.csv. And after I read this in, I can show you here just a head command on this. That in this data set we have each row is a unique ID. We have the product ID, user ID, profile name, and then the real interesting stuff here is the score. So this is out of a 1 to 5 star rating, how many stars the reviewer gave this item. And then the text. It's a little small to see here, but you can see if I just do the text row and I show us the first one, it's actual text with the review that was written by the reviewer for this product. And we're going to be running our sentiment analysis on this row of data in this entire data set. But actually this data set, if I print the shape, is quite large. There are almost 500,000 reviews here. And just for time's sake, let's downsample this data set. So I can do that pretty simply by just doing a head command on this and taking the first 500 rows. And then if we print the data frame shape after that, we'll see that it's 500 rows. But you could scale up this project very easily to all 500,000 products if you wanted to run a more intense analysis. So then I'll just put the data frame head command here so we can see and reference back to what columns we have available to us. Now let's do some quick EDA just to get an idea of what this data set looks like. So we'll take this score column, which we know to be a value between 1 and 5, and we're going to do a value counts on this. This gives us the number of times each score occurs, and then we'll sort the index, and we'll do just a bar plot of this. Kind will be a bar plot, and the title is going to be count of reviews by stars. And let's also do a fig size of 10 by 5. Plot that. And let's add a label to it. So I'm going to do some line breaks here to clean this up. And we're going to call this our axis. And then I'm going to set the X label as review stars. And we will do PLT show. All right, so we can see here that most of the reviews are actually 5 stars, but then it kind of goes down. It has a little uptick in the number of 1-star reviews we have. So the very biased towards positive reviews in our data set. That's good to know before we get any further. Now, the next thing we'll do is just some basic NLTK stuff. And we'll start by just taking one example review. So let's do example equals this text column and just pick the 50th value as an example, and we'll print this example. All right, so what did this person say? They said, this oatmeal is not good. It's mushy, soft. I don't like it. Quaker Oats is the way to go. Okay, so seems to be negative sentiment here. But before we get into that, let's just see some of the stuff that NLTK can do out of the box. NLTK can tokenize this sentence. So let's take this example and run NLTK word tokenizer. And all that basically does is splits this into the parts of each word in the sentence. Now, it looks pretty clean at the beginning, but then you can see that I don't do an N apostrophe T is split. So this is a little bit smarter than just splitting on spaces in the text. And this will give us our actual tokenized results. In natural language processing, often you need to convert the text into some format that the computer can interpret, and tokenizing that is the way that you do it. So let's make this the tokens. And then take the tokens and let's just show the first 10 so we can remember what this looks like. All right, so now once we have these tokens, another thing NLTK can do out of the box is actually find the part of speech for each of these words. So let's run NLTK's POS tag for part of speech tagging, and we'll run this on each of these tokens. Now we can see that we have each token and we also have its part of speech. So these part of speech values are codes, and we can actually load up an example page that has some examples of what each abbreviation means. So let's go back here to our example, not here. So you can see that oatmeal is NN. And in our part of speech tagging, that means it's a noun, a singular noun. So each of the values in this text has now been given its part of speech. So let's call this tagged. And then let's just show the first 10 again as our example. Now it can actually, we can take it the next step from this and take these tags part of speech and put them into entities. So NLTK, we can do a chunk on this and then NE chunk. So this takes the recommended name entity chunker to chunk the given list of tokens. So it takes these tokens and actually will group them into chunks of text. So let's run it on this to see what it looks like. What are we getting here? Oh yeah, so we need to store this because we're running in a notebook, and then we'll actually run entities.pprint for pretty print of this. So you can see that it's chunked this into a sentence, and noted here that this is an organization. Some other interesting stuff about the text that can be extracted out automatically using NLTK. All right, so that's just a basic primer about NLTK, but we want to get into sentiment analysis. So we're going to start by using VADER. VADER stands for, what does VADER stand for? It stands for, I wrote it up here, Valence Aware Dictionary and Sentiment Reasoner. So this approach essentially just takes all the words in our sentence, and it has a value of either positive, negative, or neutral for each of those words. And it combines up, it just does a math equation, and for all the words, it'll add up to tell you how positive, negative, or neutral that the statement is based on all those words. Now, one thing to keep in mind is this approach does not account for relationships between words, which in human speech is very important, but it at least is a good start. So we also remove something called stop words. Stop words are just words like and the, and words that really don't have a positive or negative feeling to them. They're just for the structure of the sentence. All right, so let's do some sentiment analysis using this VADER approach. We're going to do from NLTK sentiment, import sentiment intensity analyzer. And then we're going to also import from TQDM notebook, import TQDM. This is just a progress bar tracker for when we're going to do some loops on this data. I also made a video about TQDM that you can watch if you're interested. And then we're going to make our sentiment analyzer object by calling this sentiment intensity analyzer, creating it and calling it SIA. And that's going to be what we're, the object, let me make sure. Oh yeah, this needs to be from TQDM notebook import TQDM. And now we have our sentiment intensity analyzer object. We can run this on text and see what the sentiment is based on the words. So let's run just on some examples. Let's say, I am so happy, an exclamation point. We can see that this VADER approach has made this, has tagged this negative as a 0. These are scales from 0 to 1. So 0 negative, neutral 0.3, and positive 0.682. So mostly positive. Now there's also this compound score, which is an aggregation of negative, neutral, and positive. This compound value is from -1 to +1, representing how negative to positive it is. But if you want more detail, you can take the breakdown of this negative, neutral, and positive. So it did a good job. It made this, it tagged this as being mostly positive. Let's try the opposite. So SIA polarity scores of this is the worst thing ever. All right, now we see that the polarity score for this is mostly negative and neutral, and nothing positive. And then this compound score is negative 0.62, so more on the negative side than positive. Very interesting. Now we can run SIA on our example like that we had before. Remember our example, which was this oatmeal comment? Let's run that on the oatmeal comment and see what it is. Okay, so it's pretty high neutral, but also some negative, and the overall compound score is negative, no positive score. So we want to run this polarity score, run the polarity score on the entire data set. So basically looping through this data frame we have, every text field, we want to run this and grab the polarity scores. And we can do that with a simple loop. So we're going to do for D, which is going to be just our row, or we can just say for row in TQDM df.iter rows. And then our total is going to be, yeah, so then this should work, I think. And then we're going to take the row text, and this will be our text. And then we're also going to take we're going to call it my ID, which is the rows ID column. And then let's just break here to make sure we have this correctly. Oh, that's correct. This is going to be for I row in TQDM iter rows. And then we'll also make the total of this the length of the data frame so that when we see our progress bar, it's out of 500. We're going to want some way to store these results. So let's make a dictionary called res for results. And every time we loop through, we'll take my ID, we'll store in the my ID part of the dictionary, the polarity score of the text, right? And then, yeah, that's it. Let's run this. So really fast, it ran, it's done. And now we have this result dictionary with each ID, the negative, neutral, positive, and compound score of each. But we want to store this into a pandas data frame because that's easier to work with. Let's do that really quickly by just running pd.dataframe on this dictionary. Pandas can take in a dictionary pretty easily, except for it's oriented the wrong way. So let's just quickly run a .t on this, which will flip everything horizontally. And now we have an index, which is our ID, and then our negative, neutral, positive, and our compound score for the sentiment for each of those values. All right, let's call this VADERs. That's our VADERs result. And then let's take this VADERs and let's reset the index and rename that index as our ID. So we can merge this onto our original data frame. And then we're going to take VADERs. So VADERs will now be this. And then we'll also take VADERs. And we're going to merge it on our original data frame. And how we'll do a left merge. So now basically we have our data frame, but with our scores. And we also have all the other values from our original data set, including the text. So if I run ahead on this, we can see now we have sentiment, score, and metadata. All right, so let's see if this in general is in line with what we would expect. So we're going to make some assumptions here about our data, that if the score of the item that the reviewer gave it is a 5-star review, it's probably going to be more positive of text than if it was a score of 1. A 1-star review is going to have more negative connotation than a 5-star review. And we can do that by just doing a simple bar plot. So let's use Seaborn. I think I imported Seaborn. Yeah, I imported Seaborn before. And we're going to do a bar plot of this data where our data is VADERs. Let's call this plot VADER results. And our X value is going to be the score, which remember is the star review of the person. And then compound is going to be our Y value, and that's the -1 to +1 overall sentiment of the text. Then let's set the title to be Compound Score by Amazon Stars Review. And then we'll show this. What did I do wrong here? I spelled compound wrong. Compound. There we go. Okay, so 1-star review has lower compound score, and a 5-star review is higher, and it's actually exactly what we would expect. The more positive that the compound becomes, that's the more, well, by each score that was given, it's more and more positive of text respectively. And that's good. That just kind of validates what we are looking for. We can even break this down. Instead of looking at the compound score, we can look at the positive, neutral, and negative scores for each. So we're going to do that by doing something like SNS bar plot. Data is VADERs again. X is score again. And then let's do the positive and see what this looks like. All right, so this is the positive score. And let's actually make 3 of these side by side. Left being positive, neutral, and then the negative to the right. And we'll do that with matplotlib subplots. So this will make a 1x3 grid of our results. And we will call this axes, put this first one here, which will be our positive. Then we want our neutral, and then we want the negative. And this is going to be in position 1, 2, and 3. And then let's also set the title so we remember what these are. Positive, neutral, and negative. And plot show this. Oh, this needs to be AX equals. And I need to change each of these. There we go. Now we have, let's see what we have here. Let's make this a little less wide. We have the positivity is higher as the score is higher in terms of stars. The neutral is kind of flat, and the negative goes down. It becomes less negative of a comment as the star review becomes higher. Great. This just confirms what we would hope to see and shows that VADER is valuable in having this connection between the score of the text and sentiment score, and that it does relate to the actual rating review of the reviewers. Let's do a tight layout just because I see some overlapping here of the review of the y-axis labels, but I think this is good. All right, so now we're going to take it up a notch. Our previous model just looked at each word in the sentence or in the review and scored each word individually. But like we mentioned before, human language depends a lot on context. So if I say something, we'll see, a sentence that could have negative words actually could be sarcastic or related to other words, in which way it makes it a positive statement. So this VADER model wouldn't pick up on that sort of relationship between words, but more and more recently, these transformer-based deep learning models have become very popular because they can pick up on that context. So we're going to use from huggingface, which is one of the leaders in these types of models and gathering them and making them easily available. We're going to import from transformers. Now this is Hugging Face's library. You could pip install transformers to get this on your local machine, or of course, you can just run it in a Kaggle notebook like we are right now. So let me make sure this works. From transformers, we're going to import our auto tokenizer. Now this is going to tokenize similar to what we showed NLTK can do. And then from transformers, we're going to import auto model for, let's autocomplete here, for sequence classification. You can see that there are a lot of different types of models that Hugging Face has. And then we're also going to import from SciPy special softmax, which we will apply to the outputs because they don't have softmax applied, and this will smooth out between 0 and 1. All right, special, spell that correctly. All right, and then we're going to pull in a very specific model that has been pre-trained on a bunch of data for sentiment, exactly like we're trying to do. This is provided by Hugging Face, and when we run the auto tokenizer and the auto model sequence classification methods and load it from a pre-trained model, it'll pull down the model weights that have been stored. And this is really great because we're essentially doing transfer learning. This model was trained on a bunch of Twitter comments that were labeled, and we don't have to retrain the model at all. We can just use these trained weights and apply it to our data set and see what comes out. So anytime you do this the first time, you will see that it needs to download all of the weights. This is expected. And now that's finished. Now we have a model and a tokenizer that we can apply to the text. So let's remember what our example was before. Now this is this oatmeal comment, and our polarity score from the old type of model looked like this. Let's call this the VADER results on example. Remember, negative, neutral. And we want to run this, though, on using the RoBERTa model that we've pulled. So we just need to take a few steps before we can run it on RoBERTa model. And that's first thing is encoding the text. So we're going to take our tokenizer that we pulled in, and we're going to apply it to this example and return tensors is going to be PT for PyTorch, and then encoded. Let's call this, you can see here, this is the encoded text. So this is taking that text and putting it into ones and zeros, that embeddings that the model will understand. We'll call this our encoded text. Then we're going to take that and we're going to run our model on it. It's just that simple. So we're going to take this encoded text, run our model on it, and this will be our output. And then you remember how so this is what the output looks like. It's a tensor with our results. And then we're going to take that output, take it from being a tensor, and make it into NumPy so that we can store it locally. So let's detach this and then NumPy and store this as scores. And then the last thing we're going to do is just apply that softmax to these scores that we imported. Softmax layer, like this. Now if we print our scores, we see that we have 3 different values in a NumPy array. Now these are similar to the last type of model that we ran. So basically this is the negative, the neutral, and the positive score for this text. So let's make a scores dictionary where we'll store this, and we'll put in RoBERTa. Negative is going to be the first value, and then we'll just do like this: negative, neutral, and positive, and this will be 0, 1, 2, and we'll print this scores dictionary. Need a comma here. There we go. All right, so the RoBERTa model, much more than the VADER model, thinks that this comment is negative, which from reading it seems to make sense. This is a very negative review of this product. So already here we can see sort of how much more powerful RoBERTa is than just a VADER model. Let's go ahead and run this on the entire data set like we did before with the VADER model. So we can do this pretty easily by just making a function out of the code that we did before called polarity scores RoBERTa, where it takes in an example like our code did before, and it runs all of this and it just returns scores dictionary. So now we could run this on one example of text and get this scores dictionary like we had written the code for above. And we're going to iterate over the data set just like we did before. So let's take this code from above where we iterated. And we have we're going to call this our VADER result because we'll still run the VADER text on this. And then we'll also have our RoBERTa result, which is going to be the polarity scores RoBERTa function that we had written on this text. And we'll break here after the first one just to see how it ran on the first iteration through. So we see we have our VADER results and we also have our RoBERTa results. It's exactly what we wanted. And we also want to combine these. So the way we can combine two dictionaries is there's a way to do it with the newer version of Python, but we're running an older version. So we'll just do it like this. And we'll call this both. That's both results. Let's also go and rename this from negative, neutral, and positive to be explicitly named that they're VADER results. And I'm just going to copy this code, which will basically rename these to VADER and then the key name instead of right now it's just negative, positive. And then we will combine these two. Okay, so running that for one iteration, it looks like our results look good. And we want to now just run it through all 500 examples. So I'm going to take out this break and it's going to run through. Oh, we also need to actually store this into the dictionary that we're going to store with the ID, and we're going to store both. Now I know this is going to break because I ran this before, but I want to just show as an example when it does break. All right, it did break on one of these examples because the text had some issues with it and it wasn't able to run through the RoBERTa model. So instead of debugging this all right now, and it has to do with the size of the text itself, there's certain size of text that's just too big for the model to handle. We will skip those, and we will skip those by adding a try except clause here. So it'll run through except for when this runtime error occurs. In that case, we'll just print out a message so we know that it broke for ID, this ID. Now we're going to rerun and let it go through all 500. Okay, so that's done running, and you can see that it did break for two examples. We could have lowered the amount of size of those and it would have worked, but this gets us a good result for now. Now, it was pretty slow running. Keep in mind, that's because I was running it only on a CPU. These RoBERTa models and transformer models are optimized to be run on a GPU. And if I was to go here and turn on the GPU in the preferences, I could have run a lot faster. But it works for this case just to run it on a CPU. And now let's actually take the results of this and make the results dictionary similar to what we did before. So this line of code, which takes these results, runs the transforms on it. Let's call this results data frame. And it will merge back on the main data set. Now, if I do a head command on this, we can see now we have our VADER scores, all 4 of them, and our RoBERTa scores for each row in the data set. Really quickly, let's compare scores across or between models. And we can do this using Seaborn's pair plot. I think this would be a nice way to look at it. So pair plot lets us see comparison between each observation and what each feature looks like. So I'll show you here by running it on this results data frame. And then we're just going to provide it the variables we want it to look at. And those will be this VADER negative, neutral, positive, and let's remove the VADER compound because I don't think that's really needed to compare. And we're also provided the RoBERTa columns, and we're saying these are the variables we want to compare. Let's also color it. So the hue color of each dot is going to be by the score, which is that 1 to 5 star scores. And let's also give it a palette, something where we can easily see the difference between each values. Okay, so this is VARs, I think. And actually this combine and compare is what we're doing now. Okay, so a lot going on here, but one thing that we notice here is the 5-star reviews are this purplish color. And if we look at VADER, the positive reviews are more so to the right for these 5-star reviews. For the RoBERTa model, you can see it's way over to the right. And then we can see that there are some correlations between the RoBERTa model and the VADER model. It's a little hard to see exactly if there are correlations, but one thing that becomes very clear is that the VADER model is a little bit less confident in all of its predictions compared to the RoBERTa model, which really separates the positivity and neutral and negative scores for each of these predicted values. But if you look here, this positive and neutral, like the RoBERTa model has very high scores for the 5 stars, and most of these 1 stars are very low in positivity sentiment scoring. So that's pretty cool. Let's also review some examples. This is going to be pretty cool because now that we have sentiment score and we know the 5-star ranking of the review, we can look and see where the model maybe does the opposite of what we think it should. So one way we can do that is we just take this results data frame and we query where there's a 1-star review. So score equals 1. These are all our 1-star reviews. And then we'll sort the values by this RoBERTa positivity score. And for ascending, let's make this false. So the highest positivity score with the rating of the value being 1 will appear at the top. And then we'll take the text of that and just do a values and print out the top value. So what we're looking at here is text that is said to be positive by the model, but is 1 score by what the actual reviewer gave it. It says, I felt energized within 5 minutes, but it lasted about 45 minutes. I paid $3.99 for this drink. I should have just drunk a cup of coffee and saved my money. So this is a very nuanced sentence. And you can see that it starts off being sort of positive. I felt energized. It lasted 45 minutes. The model is getting confused and thinking this is more of a positive statement than we can tell that this is saying negative by the end of the statement. So that's interesting and it makes sense. Let's do the same thing with the VADER score. So look at the most positive score for a 1-star rating. It says, so we canceled the order. It was canceled without any problem. That is a positive note. So they actually use the word positive, and without any problem seems positive, but it is a negative review. And it's being a little sarcastic, I guess, a little tongue in cheek. And the model does not pick up on that, especially the VADER type of model, which is only looking at a bag of words for all of this sentence and the score of each word individually. Let's also look at negative sentiment 5-star review. And let's do this with the RoBERTa model first. So we'll switch to a 5-star review and we'll look at the top negative sentence. It says, this was so delicious, but too bad I ate them too fast and gained 2 pounds. My fault. Okay, so it is sort of a negative sentiment, but a positive review. That's kind of funny that that one came up. And then we'll do the exact same thing for the VADER. And it happens to be the exact same one. So both models got, I guess you could say, confused, but maybe this actually is a negative sentiment for a positive review. So maybe it did a better job than what we would expect to see. All right, so we've explored a lot of things with sentiment analysis so far. The one extra bonus piece that I want to show you is just using the Hugging Face Transformers pipelines. And this just makes everything really simple. And I want to make sure I noted this. You can read about it on their website. But you basically can just import from Transformers library a pipeline. And you need to spell pipeline correctly. There we go. And then we can make a pipeline called sentiment pipeline with this pipeline. And there are a handful of things that we could feed it that it will automatically be set up, tasks that it's automatically set up for. And we want to do sentiment analysis. This will automatically download their default model and embeddings for this pipeline, and you can just run sentiment analysis with 2 lines of code. Super quick and easy. You can also go in here and change the model that it uses and the different tokenizer, but the nice part about this is you don't have to set anything up. You just do this. It'll download the model. It'll give us our default sentiment pipeline, and then we can just run text on it. Okay, so that's done running. So I could say, I love sentiment analysis. And you could see it's a different format in the output it gives by default, but it's saying this is positive with a very high confidence. I'm going to type in, make sure to like and subscribe here. And that also is positive. Just to do a bad example, we'll say boo. And that does show as negative, so it's working. All right, so that's it for our sentiment analysis project tutorial. So there we have it. We walked through 2 different types of models that you can use for sentiment analysis, explored some of the differences between them. We actually ran it on a whole corpus of data, 500 different reviews from Amazon. You could scale this up and run it on all 500,000 examples and see what insights you can find. So thanks again for watching my videos. Make sure you subscribe so that next time I release a video, you'll be notified, and I'll see you in the next one. Bye.